or can affect. In fact, we have catalysts that can slow down or inhibit a reaction. Then the common catalysts that we know, they increase the rate of reaction. Okay, so they speed up the rate of a reaction by changing the mechanism. Okay, so catalysts, we know they speed up speed up the rate of a reaction by changing the mechanism. Okay, so these are some of the factors that affects the rate of a reaction. But our main goal here in chemical kinetics, we want to measure the rate of a reaction. Okay, so now let's see how we can measure. Let's see how we can measure the rate of a reaction.
Sir, before you proceed, I have a question.
Let's say
Yes. Can you kindly repeat what you said about concentration of the reactants?
concentration of the reactants. As the concentration of the reactants increase, so does the likelihood that reactant molecules will collide. I think that's what I mentioned. Okay. As the concentration of the reactants increases, so does the likelihood that reactant molecules will increase. As as the concentration as the concentration of the reactant increases, so does the likelihood so does the likelihood that reactant molecules will collide. Okay, I'm sure it's clear now. Okay, so that's about the concentration of the reactants. Okay, so the higher the concentration, the more the molecules will collide, just like for temperature. Okay, so now let's look at the reaction rates. Okay, so reaction rates can be determined. Reaction rates or rates of reaction or reaction rates is just one and the same. Okay, reaction rates or rates of reaction. Okay, so rates of reaction can be determined by monitoring the change in concentration. The change in concentration of either reactants or products. Okay, so we shall monitor the change in concentration. The change in concentration of either reactants or products. Okay, so we know that as the reaction proceeds, we know that the concentration of the reactants decreases and that of the products increases. Okay, so we shall monitor change in concentration of either reactants or products with time. Okay, so now we can define a rate as rate is equal to delta A over delta T. Delta A over delta T. So in this case, A can be a reactant or a product. So now, this delta means change in a quantity. Delta means change in a quantity. Change in a quantity. Okay. Then you can see here we also have some square brackets. Okay. The square brackets indicates concentration in mole per liter. Square brackets indicates concentration in mole per liter. Mole per liter just the same as molar. So we can use mole per liter or molar M like that. Okay. Mole per liter or molar. So now I'll give an example of the decomposition. Let's look at the decomposition of nitrogen dioxide. Decomposition. So let's consider the decomposition of nitrogen dioxide. NO2, that's nitrogen dioxide. Okay, so nitrogen dioxide will decompose. Nitrogen dioxide. Okay, so now we can this reaction can be carried out. It can be carried out. It is carried out at 300 degrees Celsius. Okay, so in this case, the concentration of with time, the concentration of nitrogen dioxide decreases with time. Then the concentration of nitric oxide increases, and that of oxygen also increases. These are the products. Okay, so reactant concentration decreases, oxygen. Now look at the mole ratio. The mole ratio of nitric oxide to oxygen, it is what? 2 to 1. 2 to 1. So which one will increase more? It's the nitric oxide which will increase more. So we expect this graph to go like this. Okay, so this is for NO. Then oxygen is 1 to 2. So this one will be now, it will be under, it will be lower than the concentration of nitric oxide. It is 1 to 2. So for oxygen it can be somewhere there. Okay, so the graph would look like that. Okay, reactants decreases, then the products increases. Okay, so now we can calculate the change, or first of all let's define the rates. Okay, so in this case, since we are dealing with chemical reactions, we are dealing with the concentration. Okay, so reaction rate is defined as the change in concentration of reactant or product with time. Okay, so now or with time or per unit time. So now rate is equal to concentration of A Rate is equal to concentration of A at time T2. Concentration of A at time T2 minus concentration of A at time T1. Okay? Concentration of A at time T2 minus concentration of A at time T1 over T2 minus T1 over T2 minus T1. So this means now rate is equal to delta A over delta T. Okay, so delta means, so here now we can say rate is equal to change in concentration of A over change in time, Okay, so the change can be positive. The change can be positive. Positive means increase. The change can be positive, increase means increase, or negative. Negative means decrease. Okay, so we can have a positive change or negative change. However, for convenience, we will always define rate. As a positive quantity. So rate will always be defined as a positive quantity. Rate will always be defined as a positive quantity. Okay, so we shall look into that. This one, you'll see when we have an example why we shall always define, because we know rate can be positive or negative, but it is customary to represent or to present rate as a positive quantity. Okay, so since we shall always be looking at the rate of reactants, and we know that, okay, let me not talk much about that. Let's have an example so that you see what I'm talking about. Okay, because sometimes you may be just talking, you don't know what is happening. Let's have an example. So we want to calculate. Okay. So for the
sir, just before you proceed. Yes, on decomposition of nitrogen dioxide, was it an example, a factor, or what?
Decomposition of nitrogen dioxide?
Yes.
It's the one I'm writing right now.
No,
so let's
like
have
where you wrote decomposition of nitrogen dioxide, is it under, it falls under the factors or what?
No, it's just independent. I was just showing you how it decomposes. I was just explaining it to say the concentration of nitrogen dioxide decreases while that of nitric oxide increases. Okay, it was just an example. I was just trying to illustrate. It's clear?
Yes, sir.
Okay, so now example, the reaction, the decomposition of nitrogen dioxide carried out at 300 degrees Celsius. So this reaction was carried out at 300 degrees Celsius. The results are as follows. Results are as follows. So let's have some results. So we have time. We are going to draw a table, time in seconds. Then concentration of nitrogen dioxide, concentration of NO. Then here we have concentration of oxygen. So a table will look like that. Okay. So at time zero, the concentration of nitrogen dioxide is 0.0100. Okay. Then at time zero, we expect at time zero, it means the reaction has not yet started. So the reaction of the products is 0. Okay. So we start with 0.01. Then at 50, after 50 seconds, the concentration of NO2 now is 0.0079. Then the concentration of NO2 is 0.0021. Concentration of oxygen 0.0011. Okay. Then at 100, the concentration of NO2 now is 0.0065. Concentration of NO 0.0035. Then concentration of oxygen 0.0018. At 150, the concentration is now 0. Here, the reaction has not yet started. You can see the concentration of NO is 0. Concentration of oxygen is 0. But after 50 seconds, what has happened? The concentration of NO2 has done what? Has started reducing. Okay. So here we have 0.0079. Here now the concentration of NO, it has increased 0.0021. Then this one is half of that. Since the more ratio is 2 to 1, 0.001. At 100, 0.65. You can see 655548. Here 21354552. 11182326. Okay, so clearly here you can see that the concentration of the reactants decreases and that of the products decreases and that of the products increases. Okay, concentration of NO2. Concentration of NO2 decreases. Concentration of NO and the oxygen increases. That's what is happening here. So reactants decreases, products increases. So now we can calculate now. Let's calculate from these values that we have. We can calculate the concentration. Let's calculate the concentration of NO2. Okay, so calculate the concentration of nitrogen dioxide. Calculate the concentration of nitrogen dioxide for the first 50 seconds. So we are going to write the formula. Solution. So you write the formula. Rate is equal to, I said calculate the concentration. Calculate the rate, not concentration. You can change that. We are looking at the rate. Since we have the concentration, so we want to calculate the rate. You can correct that. calculate the rate of any O2 for the first 50 seconds. So in this case now, we are going to write the formula for rate. Rate is equal to, so in this case, it will be equal to, rate is equal to delta NO2. Delta NO2 over delta T. Okay. Rate will equal to delta NO2 over delta T. So now, delta, remember, we mentioned that rate, it will be concentration at T2 minus concentration at T1. Okay, so in this case, the concentration of NO2 at 50. So it is the final concentration minus initial concentration. So in this case, we are looking at 50 and 0. Okay, so final concentration. So we are going to say, which is equal to final concentration in this case is what? At 50 is 0.0079. So you write 0.0079 mole per liter minus concentration at T2. Concentration at T2. Concentration at T2 minus concentration at T1. Remember, it is T2 minus T1. So just the same as the final minus initial. So at T2 now, which is at T1, which is the initial concentration, which is at 0.0100. So you write here 0.100 mole per liter. Okay, which over T2 minus T1. So T2 here is what? 50. T1 is what? 0. So it is 50 seconds minus 0 seconds. Okay? Times 10 to the power negative 5. So the units now will be mole per liter second. Or if you're using molar, it will be molar per liter, like that. Okay, so you can see here that the rate is negative. We have found negative 4.2 times 10 to the power negative 5 mole per liter second, or molar per second, or molar per second. Okay, so note that since the concentration of NO2 decreases with time, delta NO2 is negative. Since the concentration decreases with time, delta NO2 is negative. Is a negative quantity. Is a negative quantity. Okay. Then, because it is customary to work with positive rates, we define the rate of this particular reaction to be, okay. So remember, we mentioned that we shall always define rate as a positive quantity. Okay, so it is customary to define rate as a positive quantity, So now, since it is customary to define rate as a positive quantity, we are now going to write the rate as rate is equal to negative negative delta NO2 over delta T. Okay, why have we introduced the negative? So rate now, we shall be writing rate as negative delta NO2 over delta T. Okay, so now this negative will cancel with that negative. Will cancel with that negative. So if the negative cancels, they will multiply to give a positive rate. Okay, so now even if it is a negative rate, we shall always present it as a positive quantity since rate is negative delta. So in this case, for a general reaction to be rate is equal to negative delta A over delta T. Since we know that the negative will cancel, or you can just write delta A over delta T. But if this negative should not appear, you present it as a positive quantity. Hope it's clear.
Yes, sir.
Yeah. We shall always present. There's a question?
Yes, what topic is this?
What?
What is the topic that you are teaching?
You don't know the topic that we are looking at. It's
No,
chemical kinetics.
Oh, okay, thanks.
So another question.
Yes.
When you say the rate, what the rate of what? What rate are we talking about?
Is that a question or a statement?
It's a question. You are saying calculate the rate. Now I'm behind the rate of what?
Can't you see what is written here? You read what is written here on the board.
The rate of NO2.
Yeah, that's what we are looking at.
Is it always that the rates are supposed to be positive?
Remember, you are not getting what I'm saying. We are saying rate can be what? Can be positive or negative. Rate can be positive or negative. Positive means what?
Increasing.
Increase. Then negative means it's decreasing.
Yes.
Okay, but we are going to present the rate. We are going to present the rate as a positive quantity to avoid. So, like this example that I've given you, what is the rate here? It is negative 4.2 times 10 to the power negative what? 5 mole per liter second. So what does this mean? It means since it is a negative rate, it means the concentration of NO2 is doing what? Is decreasing. It is decreasing. Okay. Then I mentioned to say it is because it is customary to work with positive rates. We shall be working with positive rates. We work with positive rates. It is customary to work with positive rates. So we are going to write the rate as rate is equal to negative delta NO2 over delta T. So this negative that we have introduced, it will cancel. Remember the rate that we found is this one. Remember? So the negative times negative will give us positive. So we shall always work. We always work with positive rates. It is a tradition. We always work with positive rates because this negative that we have, since we are dealing with a reactant, we know that the concentration of the reactants decreases and it will give a negative rate. So we are not dealing with the products here. It is a reactant. So we introduce this negative so that it cancels with the negative rate to give a positive quantity. Okay, so it is customary. We shall always work with the positive quantities, positive rates. So rate will always be positive. So even if here we found the negative rate, then this negative will multiply with that negative to give a positive. So always give a positive rate. But we know that it is decreasing because it is a reactant. So there's no need of showing it. So if you don't show this negative, it means that negative rate will straight away cancel since you know there's a negative. So I was saying you can even just write rate as rate is equal to delta A over delta T. But that negative, it is there. Then the answer that you are going to find with a negative, just cancel it. Since you know that there's a negative there, it will just cancel. What we want is a positive rate. Work with positive rates. Hope it's clear.
Very much, sir.
So,
So, final.
So now let me just continue before. Let me write something. So that is rate. Okay. So we shall always work with positive rates. Then also you need to know how to calculate the slope. I'm sure you do this in math. Okay. Slope of a tangent line. Slope of a tangent line. Slope of a tangent line is what? It's gradient, right? So also gradient, you know the slope of a tangent line is equal to change in y over change in x. Over change in x. This is how we calculate the slope. Change in y over change in x. So for example that we have looked at, change in y is a concentration. So we are going to say delta NO2. Delta NO2. Then change in x is what? Time, which is delta T. So you can see that. So slope of a tangent line is equal to change in x over change in y over change in x. So change in y is a change in concentration. Then change in x is change in time. But rate is equal to negative delta NO2 over delta T. Okay, so now you can see the relationship that is there. Okay, rate is equal to negative delta NO2 over delta T. So now it means that rate is equal is equal to negative rate. Let me just write this. So it means now rate is equal to negative slope. Rate is equal to negative slope of the tangent line. Negative slope of the tangent line over t. Okay? Rate is equal to negative slope of the tangent line over t. So you can see clearly here that slope of the tangent is equal to delta NO2 over T. Okay, then rate is equal to negative NO2 delta T. So you can see the relationship that is there. Okay, so rate, there's a negative, then slope of the tangent line, there's no negative. So it means now rate is equal to negative slope of the tangent line over t. So we can even calculate.
I don't have power to start combing my hair. To go to campus. Esther. Yeah, you're going. Valentine, I'm confused because me asked me, do you want online or physical? I don't know why he asked you. I know he doesn't ask. He never asked me. Oh, because he asked me. Then I said, I want online classes.
The one talking, you are disturbing us. Mute your mic.
So time is up.
Okay. All right. Okay, so we shall continue from here when we meet. Okay.
All right.
Okay.
All right.
Okay.